So in this activity, we will explore approximations and round of errors. Okay, so what we would like to find out here is um, how approximation first is done. Okay, or at what points is approximation done on your data. Okay, basically yung input nyo dito, your numerical inputs here are considered data. Okay, although we will not use the term or the name data or the term data much more often here. Pero basically that everything that you use in your computer as part of computations can be considered as data. Okay? Um but this approximation are basically necessary. Okay. One thing that you have to remember is that while some of the discussions here may give the impression that that approximation is bad uh, for computations or for everything. Okay, for dito sa context ng pinag-uusapan natin. It is not actually bad. Okay. It is actually necessary. Okay, so we will discuss this in this or you would be able to learn in this one of the things that you will be able to learn is that how approximation is done. Okay, who does it? Okay, pero binanggit naman dito kung sino gumagawa nun. Okay, and why is it necessary? Why is approximation necessary? Okay. Second thing is that I would this activity would present the idea of errors. Okay. So basically, okay, approximation when used in your data would lead to error. Okay. And again, error would seem bad. Okay. And it would just error when we discuss error would really seem bad. Okay, just as yung thinking natin at first about approximation. Okay, but as approximation is necessary, error is inherent. Okay. Um meron talagang magiging error yung numerical computations natin when we use computers to do that. Okay? And in that case, ang goal natin is to actually know okay, the nature of this error, okay? And how we can actually control them and mitigate the its effects on the result, okay? Which would lead us to have at least an idea of how can you be confident about the results um of your computations, of your numerical computations using a computer. Okay? So, ayun, pag-aaralan natin 'yan. We'll try to study uh sources of error. Okay, saan nanggagaling yung error? Paano siya nagma-manifest sa results? Okay. And then pag-aaralan natin yung tinatawag na true at saka approximate error. Okay, which are criteria in saying how much the answer is actually close to what we to a reference or a benchmark quantity which we are considering or is under consideration. Okay. Um, this activity would also like to present the general approach in writing iterative algorithms. Okay, which itong mga iterative algorithms na to is something that would be very common in future topics, in future numerical methods that we will study. Okay, so marami sa mga pag-aaralan nating there are many numerical methods that employ iterative methods. Okay? So, as of this at this point, you really need how to see how an iterative algorithm is written out in its most basic sense. Okay? And we would also talk about um some example scripts that implement iterative algorithms. Okay? Um the aim is or the ultimate aim is that later on you would be getting used to in this you would be getting used in writing these iterative algorithms so that if you are to write them on your own, okay, you would be able to start from something, okay, and then from there develop and tweak and develop your algorithm, okay, in so that it would meet whatever requirements you need to meet. Okay? So, yeah. Then number 4, present issues and uh, potential pitfalls that one may encounter when performing numerical computations using computers. Okay, so these are the objectives of the activity. Okay, so either you use MATLAB here or you use Octave. Okay, whether you use the desktop version or the online version, I think everything here would actually work. Okay, so yeah. Now let's try to do some discussions. Okay. Approximation is a process that we always do whenever we handle numerical data. Okay. We always do approximation. Okay. We always do approximation. For example, when you do your when you solve problems, okay, or when you in your quizzes or in your exams in many of your courses and even during high school and elementary years. Okay. Most of the time you are doing approximation even if you're not aware of it. Okay. For example, when you say have computed 2 pi manually, okay. When you have computed 2 pi, you might have tried operating this as say 2 times 3.14159. For example, that's how you use that's how you uh, write pi before. Okay. Um Here, okay. Dito pa lang sa part na to, we already did an approximation. Okay? We know for a fact that this one is not the exact value of pi. It is not the exact value of pi. In fact, if you what we know about pi is that pi is a non-repeating, non-terminating decimal number. Okay? It means that this number has no end. The number of decimal places in this number is infinite. Okay? It has an infinite number of decimal places. Okay? So for you to change the value, okay, and use, say for example, 4 decimal places, or basically in this case, 5 significant figures, okay, for you to use only 5 significant figures out of the many that this pi has, then that means you approximated pi. Okay, dun pa lang na-approximate yun na yung pi. So when you compute this, say for example, this becomes 18, 1, 11, 1, 3, 8, 2, then 6. Okay? So your answer is 6.28318. Okay? You come up with what we call an approximate answer. Okay? And therefore, kung approximate answer yan, that approximate answers, that approximate answer actually contains some kind of an error. Okay? So, dun pa lang, okay, dun pa lang sa idea na yun, you should have an idea of what approximation is. Okay? And when approximations happen, okay, and what effect does the approximation have, okay, on the results when we use these approximated values on operations. Okay? So, halimbawa, you use calculators, okay? This is a very routine work that we always do. Okay? When you use calculators, you only use a few number of places or few number of digits to report your answer. Okay? Yung sagot ng calculator ninyo, only a few of those digits are used in order that is reported on your paper. Okay, which is something that which is where approximation happens. Okay? As long as you don't report the exact value of a number, that's approximation. Okay? Whenever you do whenever you um, use a value that you may claim close to the original value, or what we say, shall we say, the exact value. Okay. As long as you do that, you are doing approximation. Okay. And when numbers are approximated, okay, a discrepancy between the actual number and the approximated number will be produced. Ito yung sinasabi ko kanina. Between pi and 3.14159. Even if I use the next numbers there, and say for example, I use 20 decimal places, still, I am approximating pi. Okay? I strictly am approximating pi. Okay? And therefore, I am producing some kind of a discrepancy between the exact value and the approximate value. Okay? So, this discrepancy is called an error. Okay? And the analysis of these errors is an absolutely necessary matter of discussion whenever computers are used for handling numerical calculations. Okay. This will be this sentence, the motivation by which we study errors in numerical calculations will be made more clear or made clearer later on. Okay, especially when we talk about how uh, the errors, okay, how errors can be used as a criteria in order to express how confident we are with the answer. Okay, so as I said earlier, generally speaking, approximating numerical data is not at all bad. Okay, it is most of the time necessary, okay, for both the users and the computers that perform the calculation. Sa side ng user, okay, sa side ng user, of course, we cannot, for example, if you I ask you to write pi, you cannot write pi in using non-repeating, non-terminating decimal number. Okay? For one thing, hindi nyo maalala lahat ng digits niyan. As I remember it now, hanggang 5 decimal places lang ako. That's how many places I can remember out of 5. Okay. A computer program can be used to generate 1,000 number of decimal places. Okay. I forgot what was the record. But there is a record number of decimal places that is known to pi. Okay. And again, that's just an approximate value. Okay. Even though you use 100,000. Okay. But we know for a fact that it is much closer to the exact value than 3.14159. Okay. As you actually increase the number of decimal places, you actually go towards the exact value. Okay. You are approaching the exact value as you increase the number of decimal places here. Okay. So that's for the user part. For the computer part, actually same thing. But this has something to do, okay? This is something to do with their limitation, okay? In terms of storage and memory. And of course, their circuits. Okay. Now, you might have been able to study this in your computer fundamentals, but one idea that you should have learned there is that computer is a digital device. Okay. So computer is a digital device. It means that its circuitry operates on a digital mode. Okay. And when we say digital mode, it means that all data, okay, all data are stored, okay, all data are stored in a finite memory. Okay. So which it means that there's a limitation as to how much data can we actually save in this finite memory. Okay. So that is why one thing that you have studied in your computer fundamentals is that this data are actually expressed as binary. Okay? Meaning it's a number system containing two numbers, binary. Means two. Okay? This number system contains two symbols, namely 0 and 1. Okay? And then everything is expressed in terms of these two numbers. Okay? So now, since meron ka lang finite na memory, okay, then there's a finite number of binary digits, okay. There's a limit in how many binary digits you can actually use in order, say for example, to represent your data. Okay, so even if your data is, say for example, a decimal number, okay, that gets converted into another number, okay, which uses the system, uses a binary system, okay, and there's a limited number of binary digits, or this is what we call bits, okay. There's a limited number of bits that you can actually use to do that, okay. So so meaning it also means that that computers should be able to should be approximating some of your numbers also because of this limitation. Okay. If your computer also cannot represent pi fully. Okay. Although it can compute everything, but it cannot really represent pi in a very in its exact value. Okay, again, even if the number of terms, if the number of decimal digits has been increased to kahit ma 1 million pa yan, it's not the exact value. Okay? So, both computers and human, okay, the human user of computers, do approximation. Okay? And for a very good reason. Okay? Um, although we recognize that there are cases that this approximation are done so bad, okay, either by the computer or by the user, okay, cal- calculations would produces unexpected, erroneous, and misleading results. Okay, this is where the notion that even if if your program has an output, it doesn't necessarily mean that that output is correct. Okay, you don't necessarily jump if you execute your program, or if you execute your script, and there appears that message no error message has been communicated back to you by your programming language, or by the compiler. It doesn't mean that the results is actually correct. Okay, you still have to dig in deeper, okay, in order for us to determine whether that answer is correct or not, because it might contain your program might be containing some hidden errors that we don't that doesn't really um, come up when the program compiles, okay, but lumalabas din itong mga errors na to, okay, dun na sa results mismo. Okay. These errors come on or manifest on the results. Okay. So that is why you should always be careful with this one. Okay. Again, the notion is um, when your script executes without errors, okay, it doesn't necessarily mean that the answers it produce is correct. Okay. You have to dig in deeper. You have to analyze further. Okay. Whether you can accept that answer or not. Okay. The need for correct and accurate results from computations necessitates the awareness of issues in and around the process of approximations so that their effects can be known, predicted, and controlled. Okay? So, this need increases dramatically, okay, when these results are to be used for solving real-life problems in engineering, medicine, economics, and other sciences. So, if you're using computer methods in order for you to calculate something, okay, and that calculation actually involves a real-life problem in any of those fields, okay, then you must be more aware of those issues with regards to approximations and errors, because they can determine, for example, life or death, okay, or low cost and high cost, cheap or expensive uh, costing of your product, or something that you need to buy, for example. So you have to be aware of these issues. No, at this point that we are starting to study numerical methods. Okay. So as I mentioned earlier, we can look into the approximation done by the computer, and we can look into the approximation done by the user. Okay. So let us start studying approximations in computer number representation. Okay. So as you may have been well aware in your computer class before, again, numbers in decimal are not the numbers that your computer interprets it to be. Okay. The number 10 in decimal, okay, or the number 10 in base 10 is not the same number, okay, when represented in computers. Okay. For one thing, this 10 is represented in different ways depending on the system, okay, or the system used, okay, in order to represent numbers. And a computer can actually use different types of system. Okay. For example, computers can represent numbers in terms of integers. Okay. And these integers have different forms. Like for example, int 8, int 16, okay, int 32, int 64. Okay, the numbers here, okay, represents how many bits are to be used to represent the number 10. Okay, for example, so in int 8, number 10 can be represented as 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0. Ay, sorry, 1, 0, 1, 0 pala. Mali pala ako. Ayan, 1, 0, 1, 0. Wala na yung 0 dun. Okay. So, there. That's how you represent 10, for example, in integer using 8 bits. Okay. So, there is a limit of number of bits there. Okay. There's a limited number of bits here, which is 8. Okay. And as you can see, this number can only represent a certain range of numbers. Okay. So that's one system that your computer can use. Okay. Another system is that they can also represent unsigned integers. Okay. By the way, yung ginagamit kong term dito in terms of representation, or yung tawag sa representation nila, are actually terms used in MATLAB and in Octave. So MATLAB and Octave also use int 8, int 16, int 32, int 64. You may actually recall this in your activity 0, okay, under data types. Okay, under the topic of data types, there is a discussion there that involves the numerical classes or numerical data classes inside MATLAB. And actually that also applies to Octave. So you have integers there, you have unsigned integers there. Say uint 8, uint 16, uint 32, uint 64. Okay? So you have those kinds of Okay. And then still you have what we call the floating point numbers. Okay? So since this one and this one are integers, it means they can only represent full numbers, or in the case of integers, positive, 0 and negative numbers only. Okay? For in the case of unsigned integers, it has 0 up to and positive numbers that it can represent. But in both cases, it cannot represent numbers with fractional parts. Okay? And those numbers are represented using floating point representation. Okay? And floating point representation has two systems under it. Okay? We have a single precision, okay, and double precision. Okay. Precision here actually pertains to parang measure siya of how close each number can be represented. Okay, later on pag-uusapan pa natin siya, which would really give meaning to what precision here means in the context of floating point numbers. Okay? But here what we would discuss is what we call yung double precision floating point numbers, or By the way, in some literatures, and not in MATLAB actually, pero in some literatures, single precision floating point numbers are is written as um, float 32. Okay, and global precision is written as float 64. Okay, these are not MATLAB terms. Ulitin ko lang, these are not MATLAB terms katulad nitong mga to. Okay, these are MATLAB terms. These are not. Okay, kasi baka mamaya i-issue yung command na float 32 tsaka float 64 dun sa sa MATLAB niya. No, they won't work. Okay. I would just like to use this, okay? Because it really the term single precision floating point numbers, okay? Single precision floating point numbers and double precision floating point numbers are actually mouthful. Masyadong maraming kailangan sabihin para lang ma-convey ko yung idea. But when we say that that is float 32 and float 64 respectively, then mas madali siyang at alam natin kung ito yung tukoy niya. Okay? Now, um to be able to discuss, okay, to be able to discuss where approximation happens, okay, um we we first try to talk about how double precision floating point numbers are, or how floating point numbers in decimal are represented using using float 64. Okay. Number one, um double precision floating point numbers are represented using 64 bits. Okay? So that is why it has 8 bytes of information. Okay? So, ayun. Now, yung 64 bits na yon has the following code word. We call this code word. When you have when you have a binary number, okay, say for example 011 0111 0111 011011, and this number has a meaning, okay, in computers. Okay, if this actually represents something, okay, this is what we call a code word. Okay, we call this a code word. Okay, and how many bits, okay, do this code word have is what we call the word length. Okay, we call we use the term code length, okay, to refer to the number of bits of a code word. Okay, so again, if this binary number holds a meaning in your computer, meaning that your computer can interpret these numbers readily, okay, it is a code word. Okay, and how many bits does this number contain is what we call its word length. Okay, now um so the code word for your for your float 64 representation has 64 bits. Okay, and these are their composition. They are divided into three, okay, with different lengths. Okay, so here we have a single bit, okay, um is called the sign bit, okay, S. Okay, then we have an 11 bit exponent field, okay, from 60-second down to the 50-second bit. Okay, so that's 11 bits of uh, code word. Okay, and then the rest, okay, is the mantissa. Okay, or literature some literature call this the fraction. Okay, so the mantissa is 52 bits. Okay, occupying the 51st bit until bit 0. Okay, so yun yung composition niya. Okay, now any number, here's what you have to remember about floating point numbers. Okay, any number represented in the double precision floating point representation has the form plus or minus m times 2 raised to e. Okay, where m and e, okay, the mantissa and the exponent respectively, are in binary form. Okay, whose number of bits are 52 and 11 respectively. Okay, so this is the this is the form of your number, okay, in a mathematical notation, okay. But when you write this on a on a code word, this is just a bunch of one and zeros, okay, whose number of bits is 64. Okay, so that's how we interpret this kind of code word. Okay. So how do we do that? How do we go through with each of these Okay. The sign bit is 0 for positive numbers and 1 for negative numbers. So it's a straightforward thing. If the number is positive, you assign the sign bit 0, while 1 for if the number is negative. Okay. Next, the exponent field represents the power by which the base 2 is raised here. Okay. Um, what happens here is that if you have a number, okay, if you have a number there, you would have to convert that number into its binary form. Okay, you would have to convert the binary number into um binary form. Okay. I hope that you remember how to convert numbers in binary form. Okay, including that contains those that contains ano ba ito? Fractional parts. Okay. For example, you have something like 3.25. How do we convert this to binary form? Okay. We actually separate them. Okay. We do the whole part separately with that of the fractional part. Okay. So for the whole part, you do division. Okay. For example, in order for you to convert 3, okay, you have to divide 3, okay, by 2, okay, and come up with a your normal notation here must be something like 3 divided by 2. Okay, so you come up with a quotient of 1 here, and then you have a remainder of 1. Actually, what would you get is this 1 here. Okay, ang kukunin niyo is yung remainder. Okay, so you would have something like this is 3.25, no? Okay, so you would have something like so let's convert 3. Okay, so you would have something like 1 here. Okay, and then get this 1, the quotient, and then divide it by 2 again. So this becomes 0. Okay, and then 1 minus 0 is 1. Again, you get the remainder. Okay, and then you place it here. Okay, itong last na natin, this one becomes the most significant bit. The last remainder becomes the most significant bit, while the first remainder becomes the least significant bit. So this is the most significant bit. Okay, wait lang. Okay, so this is the most significant bit, while this is the least significant bit. Okay, again, yung first remainder is the least significant bit, while the last remainder becomes the most significant bit. Okay, so this is now 3 on base 2. Okay, now how about 0.25? Okay, yung 0.25 na yan, since fractional part siya, instead of using division to convert it into uh, into binary form, is that we use multiplication instead. Okay, so here's the process. Here's the process. So this is 0.25 times 2. That is 0.5. Okay. So that is 0.5. Okay. So, okay. Now we get 0 here. Okay. We get the whole part, which is 0. Okay. And then we get the fractional part, which is 0.25, 0.5. Now, this is what we will multiply again with 2. Okay, we will multiply it again with 2 and produce 1.0. Okay, we will produce 1.0 for that. Okay, so now we get the whole number, which is 1, and then get the fractional part, which is 0. Okay, then multiply it by 2. So that becomes 0. Okay, and we only stop when this becomes 0. Okay? So now, this 0 and 1, the whole numbers that we obtain is now the decimal part of your binary number. Okay? But the first whole number that you have obtained is the number closest to what we call the radix point. Okay? In decimal, in decimal system, we call this number the decimal point. Okay? But in binary, we don't call it as decimal point because decimal point is in decimal system. Okay, that should be obvious. Okay, but if we are dealing with other bases, if we are dealing with other bases, we call that point the radix point. Okay, we call that the radix point. Okay, so the first number that the first full number that you are getting here is the number that is closest to the radix point. Okay, so which means that if we write this number, okay, if we write 0.25 here of base 10, okay, if we write this in decimal, if this is the radix point, okay, let's put in 0 here para lang mailagay ko itong radix point dito. If this is radix point, this 0 here is the first 0 that you would have. Is the first number that you would have closest to the radix point, and then followed by 1. Okay, so this is now 0.25 in base 2. So therefore, 3.25 in base 10 is 11.01 in base 2. Okay, so here's the idea. If you can imagine, or if you can actually look into this process of never mind the whole number, okay, but let us try to mind this fractional part. Okay, you say that we will only be able to we will be only able to stop, okay, the multiplication process the if the answer here becomes 0. Okay, and in that case, if you are given any number, say for example 0.11, and try this process, you would be able to say that this process is actually non-stop. Okay, it would actually non-stop at a certain point. Okay, so you can actually form say 1,000 bits of this. Okay, 1,000 bits of this number in binary form. This is 0.11 in base 10. I'm talking about this one. This 0.11 in base 10. Okay. Pwede nyo simulan yan, say for example, 0.11 times 2. Okay, so that's 0.22. So the whole part there is 0. Oh, so 0.22 then times 2 is 0.44. So that is 0 again. Then we have 0.44 times 2. Then that's 0.88. Okay, that's 0 again. Okay. And 0.88 times 2 is 16.1, 17.1. So that's 1.76. So we have 1. Then we have 0.76 here times 2. Okay. If you actually continue with this process, you would be not stopping anytime. Okay. So here's the thing. If you're actually converting this, say for example, 11 that 11.01 to the base 2, and we want to convert it in a float 64 representation, the first step there is to actually move the radix point so that this becomes a number in scientific notation but in base 2. Okay, so the rules of your scientific notation is that there's only a in decimal. Okay, the number in scientific notation, ang rule nun is that the number here, say this is 4.26 times 10 raised to 4. Okay. Ang rule nung natin, scientific notation natin when we convert this is that this is only a single digit. Okay, this is a number that is between 0 and let's call that digit x, okay, and 10. Okay. Full number ha. Okay, so which means either 0, 1, 2, 3, 4 hanggang 9 lang siya. Okay? Yung number na nandito kasi nga dapat single digit lang siya. Same thing with binary. Okay, when you move this radix point, it is so that this number becomes only a single bit here. So if you do that, you would have the number 1.101 there. Okay. I moved the radix point from here to here. Okay. And then, I would have to multiply this by 2. Okay. Remember, if you have 426 times 426 and you want to convert this to um scientific notation, the decimal point here would be moved 1, 2. Okay. And then you would have to write this 4.26 times 10 raised to 2. 2 here means the number of decimal places you use to move you use so that you can move the decimal point from here to here. Okay? Same thing with this one. Since I moved this, okay, I moved this with so since I moved the decimal point one place from here to here, from the radix point to here, so that I would have a single bit on the left side of the radix point, then the number of times that I move there is its exponent. Okay? But just a reminder, this one here, although it's a binary form, pero basically baka if this is another number, you would have to write this first on its decimal number or in its decimal form. Okay? So it's okay lang naman. The thing is that we are bound by understanding that this is in binary and temporarily this is in decimal. Okay. But basically, the fractional part here, this 101 here, okay, is now what we call the Mantissa. Okay. That's now what we call the Mantissa, as referred to the discussion earlier about the code word of floating point numbers. And this one is the exponent. Okay. So remember the Mantissa is 101 and the exponent is 1. Okay. Now, what do we do is that in terms of exponent, okay, say for example, that is 1, okay, katulad nung nakita natin kanina. Okay, that is exponent. Okay, that is 1. Okay. We add 1023 to that. Okay. So the result is 1024. And this 1024 is now then converted to an 11-bit, okay, 11-bit binary number. Okay. So I have a calculator. It actually converts to 1 0 0 0 0 1 2 3 4 5 6 6 7 8 9 10 11. Okay, so that's exponent in binary form, 11-bit binary form. And that would be the exponent that is written here. Okay, so aside from since 3.25 is positive, you have 0 as your sign bit. Okay, this will now be your exponent bits. Okay, and here is in the Mantissa. The Mantissa is 101, right? We will add zeros. Okay, we'll add zeros here. Okay, until the zeros count as 52. 52 ba? 52 bits. Okay, we will count 0 as 52 bits. Okay? So that's how we convert your number to floating point representation. This is where the approximation happens. Okay, this is where the approximation happens. In this case, for example, okay, in the case of 0.11, for example, as I was telling you earlier, you may want to determine this, okay, this binary, but you would know that it would not really cease to stop kasi actually the only time that it would be able to stop is if one of the decimal would actually result to 0.5. Okay, it results to 0.5. Okay, because the next product would be 1.0. Okay, and the decimal part is 0. So that's when you multiply that by 0. Okay, then that becomes the product is 0, and then that's your stop. Okay, but in other cases, reaching this 0.5, okay, will not be actually possible. Okay, so that is why most of the time itong conversion na to, okay, actually produces an infinite number of bits. Okay, now here's where the approximation goes. Since numbers like this has infinite number of bits, and remember that as we as I mentioned before, computers has a limited amount of storage for everything. Okay? So that is why ang gagawin ngayon ng computer ninyo is that instead of using an infinite number of bits for this one, okay, it would actually round it off so that the Mantissa, okay, this number would actually just contain 52 bits. Okay? Again, what would the computer do is that the Mantissa, okay, the Mantissa is rounded off, okay, to contain 52 bits. Okay? And you might have not been able to study the rounding off rules for binary numbers. Okay? But there is a rule. There are rules that are implemented or that are in place. Okay? For one to be able to round off binary numbers. Okay? We will not deal with those rules since we do not really need to convert numbers into floating point representation. I am just stating where it happens. Okay? So that is why even a simple number such as 0.11, okay, um, uh, gets to be rounded off. Okay, gets to be rounded off. Um, it's because yun nga, in its fractional form would actually require an infinite number of bits. Okay? And for you to be able to represent that infinite number of bits into a finite number of bits, okay, into a finite number of a finite storage or a finite memory, okay, you should just use finite number of bits. So therefore, for you to be able to do that, may ika-cut off ka talaga. You really have to cut off some of the bits. Okay? And computers do that in two ways. Either they do round off or they do chopping. Okay? They do chopping of digits. Rounding off, yun nga, may rules siya. Okay? Chopping of bits means simply taking off all of those bits that are not involved. For example, if you have if you have here a bit sequence of say 1011011101, and this has say for example 100 bits. Okay? Okay, so let's say from this 100 bits. Okay? You just choose the first 52 bits. Say ito yun. This is the first 52 bits. Then this gets cut off. It's chopping. Okay? That's a process called chopping. Okay? Mamaya discuss pa natin siya later. Okay? So when you chop this off, okay, again, tulad ng sinasabi ko kanina about approximation, when you use a number in place of another number that is not exactly that is not exact the exact value of that number, then you do approximation. And this is where approximation happens in your computer. Okay? And it also means one thing. Since this is a number that has infinite number of bits, and then you have to, for example, chop things off. That also gives you an idea that there is there are sets of numbers that are allowed or that can be represented by your computer. Meron lang mga numbers that your computers can represent, and may mga numbers that your computer cannot represent, precisely because there are too many digits. Okay, there are too many digits required for the computer to represent that number. So halimbawa, for example, yung 0.25 na number. Okay. 0.25 na number can be represented by the computer exactly as it is, 0.25. Okay? Yung 0.5, okay, can be represented by your computer in an exact manner, okay, which is 0.5 talaga. Okay? But pick a number in between these two. Say for example, 0.23. Okay? This 0.23 is actually not, okay, it cannot be represented by a number. Okay? There is a number very, very close to 0.23 that your computer can represent. Okay? And that number, okay, that number is allowed to be represented in the computer, but that's not exactly 0.23 when you convert it back to decimal. So there is some kind of error there. Okay, actually para mas maintindihan niyo yung point ko, maghanap kayo ng ano, you can find you can look for some websites like this one. Okay. This is a IEEE 754 floating point converter. Okay. In which it actually puts into perspective yung sinasabi ko na can only represent so much. Your computer can only represent some numbers and it can represent some other numbers. So say for example, if you convert 3.25 to floating point number, okay. I don't think this is double. Double ba to? Okay, I think this is double. Okay, basta 64 bits to. If that is double. Okay. So if that is the case, okay. If this is only 32 bits, then this is single. Okay. So yeah. Single precision, I mean. Pero makita nyo na walang error due to conversion. But if you actually use 0.11, okay. There is a certain error. Okay, because 0.11 cannot be exactly represented in the computer. Okay. What the computer can represent is this number. Okay. And 0.11 is not that number. Okay. So therefore, instead of actually representing the number in the 0.11 exactly as it is. Okay. By the way, this is single precision. Okay, this is single precision. The number or the computer would nalaman ko single precision kasi wala lang tayo. 1, 2, 3, 4, 5, 6, 7, 8. In single precision number, the number of bits for exponent is 8. Okay? Parang this is 1, 8, and then 23. Now, 23 to. So, this is single precision. Okay? So, yun na nga. As I was saying, yung 0.11, wala siya sa numbers that the number can represent in single precision floating point representation. Okay? Or in float 32. Okay? But what the number or what the computer can represent is this number, 0.01109999. And this is the closest number that is on 0.11. Okay, so therefore, since hindi mo nga mare-represent yung 0.11 exactly as it is, and you would use this number in place of 0.11, then there is an error. Okay, there is an error that would occur. The error is somewhat small. Okay, pero take note, I would emphasize later on that small error can actually lead to large error later on when we use in calculations. Okay. Now, you can also, aside from that, for us to be able to dig in deeper, okay, I actually have included a function here, okay, that converts a decimal number into a decimal number given in x, okay, into a floating point 64-bit floating point representation. Okay. So again, this is under IEEE 754 standard. IEEE 754 standard contains how numbers are represented in computers. Okay. Now, the function this function has three outputs. S contains the bit for the sign. E contains the bit code word for the exponent, and F for the fractional part or the mantissa. Okay. So I would like you to explore this program and answer the questions, okay, in order for you to understand, okay, and including the one that I have discussed earlier, okay, put into perspective this things with regards to how numbers are represented into your computer. So ayan, that's the number representation in computers. Okay. Now, you can also explore the properties of the float 64 representation by running this script. Okay, if you run this script, yung mga output niya can actually be an indicator of what are the properties of the float 64 representation. Okay, so from there, you should be able to answer question 7, 8, 9, and 10, and 11, and 12. Okay. But I have discussed here, okay? I have discussed here those properties. Okay. So since those itong part na to, okay, would actually cover your answers for question 7 to 9 up to 12. Okay. Yung mga sagot diyan yung ibang bagay na dapat na magiging sagot nyo sa question 7, 8, 9, 10, 11, and 12 are actually in this discussion. So hindi ko na siya i-discuss dito. I would like you to figure those things out for yourself. Okay? So ayan, andyan naman yung kailangan yung malaman about that. Okay. So here's the thing. The main idea of this discussion. Number one, numbers are represented using a system, okay, in computers, okay. So for floating point numbers, we use 32 bits and 64 bits to represent them as single precision and double precision floating point numbers respectively. Okay. And still there are others like integers, unsigned integers, and so on. Okay. Characters, iba rin yung representation niya. Iba rin yung system po to represent those. That's number one. Okay. Number two. Because of this, okay, because this representations has finite word length, okay, it has finite word length. It actually leads us to think that there are limitations, okay. This leads to limitations in the in the computer's representation of floating point numbers, okay. So this puts limit, okay. Maraming klaseng limits yan. The smallest number, the biggest number, and the numbers that can actually be represented. Okay? So, in such a manner, you can say that halimbawa, when you say that this is a number, okay, that can be represented into your computer, and this is another number that can be represented into your computer. The numbers in between, okay, cannot be represented by the computer. Okay, and what the computer does is, nilalagay niya yung number, for example, ito yung number na yan. Okay, what the computer does is, it actually puts that into a number closest to that number. Okay, again, either by rounding off or chopping. Okay, so ayan. Actually, that may tawag sa process na yun, in which a number, okay, is placed into an allowed number. Okay, a number that is not allowed at first, okay, is approximated, okay, so that it becomes an allowed number. Okay, that process is what we call quantization. Okay, we have a process called quantization in computers. Okay, and this thing is actually something that may encounter nyo pa. That term is something that you will be encountering in future lessons. So I hope that you remember that I was the first one who actually introduced the term to you. And this is how it goes, okay? Kasi i-introduce natin yan in a different context later on. Pero yung meaning niya, ganun pa rin. Okay? So, ayun. That's one thing that you have to remember. So, this word length introduce limitations, okay? And those limitations, okay, lead to approximations. Okay? It leads to approximations. And finally, these approximations, okay, lead to errors. Okay, and so that is how it goes. Okay, so that is one thing that I would like to point out about errors produced by the representation of your numbers by computers. Okay, so yun. Now, next we go to the part where we discuss significant figures. Okay. Now, itong significant figures naman na to, actually pertains more on the user. Okay. Because computers can actually have a certain level of precision. Okay. By the way, when you say precision in terms of ito pala yung hindi ko na sabi ko, babanggitin ko kanina na i-discuss ko. Okay. When you say precision in terms of numbers, okay, or in terms of numbers, it actually pertains to how close a number, okay, and its representation is, okay, again, a number, okay, you have a number, and that number has an exact value, okay. But if you actually represent that number in a different form, whether it's you or it's the computer, okay, if you represent that number in a different form, okay, um, how close these two are determines how precise your number is. Okay? You might have defined precision in a different course. Say for example sa laboratory course nyo sa physics or sa chemistry. Okay? Because in that case you would have to say differentiate between accuracy and precision in measurements. Okay? Um I actually those terms are actually related in terms of the number because basically a measurement is also or can be is also a number, okay, which should also have a true value kasi when you measure something, okay, when you measure something, it has an exact value. Say for example, length yan, okay. If that is a length, meron yung exact value. Pero when you actually measure it using a computer, I mean a ruler, okay, the precision of your ruler is actually not really something na that can measure um the length of that the length of that object that you are trying to measure. Okay? So, ang gagawin mo ngayon, mag-approximate ka. Okay. Now, how your ruler can actually measure the smallest possible the smallest possible interval into it determines its precision. So kung gaano siya ka-precise ng mga numbers, mag-represent ng mga numbers, that's precision. Okay? Halimbawa, ito yung isang number. Okay? Ito yung pangalawang number. Again, anything in between here cannot be represented by your computer. Okay, pwede nyo tingnan ito in terms ng ruler. Halimbawa, ito yung 1 cm. Okay? Tapos yung kasunod niya is 1.1 cm. Okay, 1.1 cm. Tapos yung mini-measure yung haba is ito. Nasa pagitan ng dalawa. Okay? So, again, ang idea dito is that hindi nyo ma-measure yan ng eksakto because wala dun sa dalawang ito, 1 at 1.1 cm, yung exact measurement niya. What you would do, ang instinct niyo is to actually approximate how long this is in terms of gaano siya, for example, kalapit dito. Or gaano siya kalapit dito, for example. Okay? Ganun din sa numbers. If your number is located here, okay, you might have to choose whether to use 1.1 or 1 cm. Okay? Now, as you may recall, okay, the larger, as you may observe, the larger this interval, okay, the larger this interval, the larger the possible error may be. Kasi ito yung magiging error niya. This becomes the error. Okay? So, pag mas malaki yan, say for example, yung ruler nyo can only measure 1 cm. Tapos pagkatapos nyo, 1.2 na. Ito yung number niyo. Okay? If wala tong 1.1 na to, in between 1 and 1.2, okay, ito yung magiging error niyo, for example. Okay, okay, pwedeng ito rin. Baka yung mas malapit yung gusto niyo. Okay? Pero still, mas malaki pa rin siya kumpara mo dito. Kung ito lang yung error mo nung una, this is now your error on the second case, in this case. So, mas malaki pa rin siya. Okay. So, ito, pag ganito yung number system mo, this is less precise. Okay, then this one. Okay. So, how close this number and this, how large is your error actually determines how precise your number is. Okay. If the maximum error or if the most error that you can introduce into your numbers when using a certain number system is of this then that's how precise your number system is. Okay? So, yun yung precision tinatawag. Again, related yan sa measurements. Okay. Now, again, in terms of significant figures, Ito naman yung sa sa part natin kasi when we express numbers, okay, especially if these numbers are approximate, um we only report a certain number of digits. I mean, you don't report everything. Okay. If your calculator brings out a result that is 4.92135741327 for example. Yan yung lumabas sa calculator ninyo. You don't report it as it is. Okay. You might report it as 4.92. That's what you would report. Okay? Kasi ang usapan niyo for example sa class is that you would just report results in using two decimal places for example. And that's the common way of expressing how precise okay you should report your answer. In this case, you are reporting your precision until hundredths digit. Okay, you are reporting your results um until the hundredths place. Okay. So that means that our number is precise on by this much. Okay. Uh, Up until the hundredths digit. Okay. So ganun yung precision ng number natin. Okay. So ayun. It's also related to how we express our numbers. Okay. Um So, yun na nga, when quantities or results of a computation are reported, we use a convenient number to represent these results. Okay. If the number representing these quantities or results contain too many digits, okay, we basically approximate it. Okay, either by truncation, okay, or ito yung in this context we will not use the term truncation no, or chopping. We will just use the term chopping off. Okay, or chop numbers. Actually in-explain yan dito sa part na to. Okay, in-explain yung term na yan sa part na to. So baka dapat supposedly dapat chop off yung lalagay ko dito. Hindi ko pa nabago kasi I actually edited these things by parts. Okay. But in any case, let's use the term chopping off in this manner. Pero basically, tama naman yung term ng truncation. Okay. There's just a purpose kung bakit chopping off yung gagawin natin. Okay. Now, when you use approximate values, okay, in expressing your numbers or in expressing your results, okay, there should be a way, okay, for us to quantify with how much confidence we have to that result. Okay. So the idea of significant figures is to put that confidence um into quantity. Okay, into a quantifiable um entity. Okay. Para malagay natin sa number kung how much confident are we in terms of how the results turned out. Okay. So, parang for example, when you say 4.92, okay, when you say 4.92, yun nga, has three significant figures. Okay. It is certain that the measure is more or less around 4.9. Kasi ito in the rules of in the rules of significant figures, when you say three significant figures, the last digit in the significant figure is actually an uncertain number. Okay, so which means itong 2 na to, okay, itong 2 na yan, pwede yang 1, pwede yang 2. Okay, pwede yang 1 or pwedeng naging 2. Actually, depending yan dun sa number na kasunod supposedly nung nung number nung 2. Okay, because when we round off here, this becomes an uncertain number. Okay, and when you say and in the rules or in the definition of significant figures, it means the number of significant figures of a number means the number of certain digits plus one uncertain digit. Okay, so which means kung three significant figures yan, dalawa dyan certain. Okay? And then the third one, which is ito nga yung place na to, yung value ng place value na to. Okay, is uncertain. Okay, kasi rounded off na yung number na yan. It's either could have been 1 or 2 depending on what digit is this. Okay? So it means now that that our answer, okay, if your answer is expressed in three significant figures, that means now that our answer has is correct to the tens place. Okay? So, ibig sabihin, sigurado tayo na yung tens place, tama. Okay, we have assurance that our tens place is correct. Okay, so, it means that, ganun lang ka-precise yung natin, ganun lang ka-precise yung results natin. Okay, that means that we are confident to say that these two numbers are correct. Okay, but we're not really sure about 2 here. Okay, so, at least we're confident that 4.9 is correct. Okay. The 4 and 9 here in this number is certain and is correct. Okay, so that's how significant figures quantify your confidence in terms of expressing a certain number. Okay, so the concept of significant figures has two important implications in the study of numerical computational methods. One, since numerical methods yield approximate results, it is imperative for us to develop criteria to specify the degree of confidence in the approximate result. So that's one thing that I would like to emphasize with the earlier discussion. Okay, by specifying that there is a certainty that the number of digits of the results is significant. Okay, which in that case is yung 4 at saka yung 9 nga. Okay, we will be able to quantify the level of confidence we have even if the result is an approximate number or is an approximate result. Okay, so we will be able to quantify that confidence. Okay, number 2, numbers that such as an infinite number of digits such as pi, e, and other irrational numbers need to be approximated because you cannot write them in computers using their entire digits or in their entire kasi nga they are non-repeating, non-terminating decimal numbers. Okay, so ayun, although more significant figures included in the approximate value is generally considered to be the better, the more significant or the more digits that you place, okay, in the approximate value, okay, the better the approximation. Okay, but the thing is that the more the numbers that you place, the more operations that your computer will perform. Okay, so therefore, babawi naman si computer. Ito nga yung number no niya. This is the number that you use. Okay, this much number you have used to represent an irrational number. Okay. But and that assures that the number is more accurate, okay, or more precise. Okay. But the computer would now be using this much operations to operate on that number. Being your number contains this much number of digits. So therefore, mas marami ang ilalagay nyo, mas accurate, mas precise nga siya. But the thing is, the computer would also use would use a certain amount or certain number of operations on your number. So mas marami yung ilalagay yung number, mas marami ding operations ang gagawin ng computer niyo. Okay, so there should be a trade-off there. Okay, between precision, okay, between your desired precision, okay, versus yung computational complexity na tinatawag. Okay, yung computational complexity. Okay. So, because you might want to increase precision. Okay, but complexity would also increase. Okay. And increasing complexity means more computational load to your computer. Okay. So, it might perform with more time. Okay, it might require more time for your computer to do the operation. Okay. So, merong certain balance, okay, between this and this. Okay. That is, you would be obtaining your desired precision, okay, but at the same time you would not make your computer compute so much. Okay. So there's a balance between these two. Okay. So trade-off yan. We call this a trade-off. Okay. So, ayun. Now, I would like you to review your past lessons on significant figures and look at these statements, okay, and see if they are actually correct, okay, and verify that they are actually consistent with what you have discussed in your previous courses. Pero ito kasi yung main idea, okay. Writing the numbers in scientific notation would actually really help you determine how many significant figures your number has. Okay. Then ito pa yung isang this is something that I would really like you to be mindful of. Okay. Especially kahit na hindi dito, kahit sa lahat ng ginagawa nyong computations. Okay. For example, you have a result. Okay. Say for example, that's 4.7 69. Yeah, 4.769. Okay, and you would like to express this result in terms of using 2 decimal places or 3 significant figures basically. Okay. Students normally, okay, would actually, okay, pag sinabi niyo 3 significant figures or 2 decimal places, okay. Students would normally express this as 4.7 because when they round this one off, ay sorry, mali pala. Mali pala yung example ko. Let's make the example, hindi pala 4.769. Let's make this 4.799. Yan. Because I would like to make a certain point. Yan. Yan. 4.779. Okay. So, ay sorry, last. 4.99 pala. 4.799. Okay. 4.799. Yan. Okay. Because students would actually, try to, if you are to express this using 3 significant figures or 2 decimal places, normally students would write this as 4.8. Okay. And this is incorrect. Okay. Again, if you're expressing your numbers in terms of 2 decimal places, you use 2 decimal places or you use 3 significant figures. You use 3 significant figures. Okay. So which means that when you express this in terms of 2 decimal places or 3 significant figures, it should be written as 4.80. Okay. Now, placing a 0 here, means that your number is actually uncertain at this digit. Okay. This could have been 0 or that could have been 9. Okay. Nagkataon lang na in this case, in this particular case, you made it 0 because the number preceding or the number to the right of this place value is 9. So that is why you made it 0. Okay. Pero since this is measurement, baka mamaya kasi mali ito. In terms of measurements, baka mali itong 9 na to. Baka hindi pala yan 9. Baka that is, say for example, 4. Which makes it 4.79. Okay? Yung sa thing kasi, when you round up numbers, okay, when you round up numbers, and your number is not, and the number that you are considering is not between, or is in between 2 allowed numbers in your system of rounding off. Okay, again, ang gagawin nyo lang dyan is ilagay siya sa pinakamalapit na allowable number. Okay, and if you actually report this as 4.8, okay, you are telling the reader that this is actually where you rounded off. Okay, it means that 8 could have been actually 4.7. That could have been 7 or 8 depending sa place value dito. But that's not the case, right? Okay. Kasi hindi naman siya, the number is not between 4.7, okay, and 4.8. Okay. The number is actually between 4.79, okay, and 4.8p. Okay. Kasi kung i-interpret natin yan na malapit siya sa 4.7, okay, ang layo niyan doon sa actual value lang, which is 4.79. Eh, ito na siya. Okay, if this is 4.8 and this is 4.79, this could have been 4.7. Yung number nyo nandito na. So, if you write it as 4.8, okay, ang interpretation dyan is either ito or ito siya. Ito yung range na kinoconsider ninyo. Whilst the number is here. Okay. So, you don't report it as 4.8. Report it as 4.80. Okay. And also, that also complies with what the rule of your approximation says, that you have to express that in terms of 2 decimal places of 3 significant figures. Okay. And yun nga, writing the number in scientific notation also eases identifying how many significant figures the number has. Okay, because especially if the written is very large or very small. Okay, you can actually make say for example the number is 299,93947, for example, like that. Okay. If you actually write this as 2.999, for example. Okay, times 10 raised to 1, 2, 3, 4, 5, 6, 7, raised to 7. Okay. If you actually rate, that's 2.99 times 10 raised to 7. You're saying that you're expressing these numbers in terms of four significant figures. It means, ito, ginagawa nyo ng insignificant. Which is okay, kasi considering naman yung value ng number ninyo, okay, this might be probably insignificant na nga in terms of the entire value of the number. Okay. Instead of actually using 8 significant figures. Again, if you want to report in the entirety of this, you might be thinking a more of like although my number is precise, okay, although my number has high degree of precision because I'm taking its value up to the ones place, okay. Pero if I actually use this to compute for computations, I am increasing the computational load for my computer. Okay, so it's actually instead of actually using the entire number of significant figures, why not cut it up to 4? Dahil most probably this number, this number might actually have a very small effect on the entire value of the number, even if that is 3,000. Okay, take note that your number is 29 million. What is 29 million versus 3,000? Okay. So that makes it that makes this place value, these numbers in this place values likely to be not really significant in terms of the entire value of the number. Okay? So you might want to do that. Okay? So there. Now, question 13 at saka question 14 actually reviews the concept of significant figures and the significant figures in terms of computations. Okay. This is something that I actually talked about earlier dun sa introduction natin. Okay. So I would like to go through answer question 13, question 14 in a manner that you understand how significant numbers are used and are generated. Okay. Most especially in terms of measurement. Okay. So then now let's proceed with error definitions. Okay. So, numerical errors rise from the use of approximation to represent exact mathematical operations and quantities. Okay. Either we approximate numbers, okay, those numbers that are involved in operations, or we can approximate operations themselves. Okay. When we do that in numbers, we call that approximation. Okay. And when we do that on mathematical procedure, we call this truncation errors. Okay, so that is why I separate the truncation term dun sa earlier natin. Although the truncation is also doon sinabi ko, when you have a number say 3.14159, and bawal na to 21347, and then you cut this one off. Okay. Cut hindi kasi gawin para mas mas significant siya. Instead of having this 2, gawin natin siyang 8. Okay. If you actually cut this one off and use the number 3.14 3.14159, okay. The process is actually called truncation. Okay, pero again, to separate this from what we will discuss in a later topic, okay, we will call this chopping off digit of numbers. Okay, so we chop these digits off from the numbers. Okay, so that's one source of that's an error that you made by approximating a number. Okay, iba pa yung round off kasi yung round off naman, this makes it 3.14160. Okay, so that is rounding off. Okay, so if you do this, okay, you are committing an approximation error because you're doing that on numbers. Okay, the other type of error that we will study in a later topic and possibly in a later activity, okay, is what we call truncation errors. Okay, yung truncation errors naman are done on mathematical procedure. If you have an exact way of determining something, okay, and then you actually have tried to eliminate some of the procedure, some of the process in order to come up with an answer, then you are truncating. Okay? And therefore, you are committing a truncation error. Common ito sa mga sa mga tinatawag nating series expansion of functions. Okay? Later on, okay, we will study marami tayong topics na pag-aaralan siya. In fact, after yung topic 3 in the lecture, okay, we will study sequences and series in the lecture. Okay. Which leads us towards what we call Taylor series and Maclaurin series. Okay. Although later on I would be mentioning these terms also again in a later part of this activity, in which it actually expands. Okay, it actually allows for expansion of some of the common functions that we use in mathematics into power series form. And as an example, we can express, for example, e raised to x, okay, as equal to the series 1 plus x over 1 plus x 1 plus x plus x squared over x squared over 2 plus x cubed over 3 pi 3 factorial plus x raised to 4 over 4 factorial and so on. Okay, leading to the general series, okay, the summation of x raised to n over n factorial for n equals 0 up to infinity. Okay, as you can see, this is a power series because this is a series in terms of the power of a certain number. And this is an infinite series because the number of terms is infinite. So we call this an infinite power series. Okay, most of Taylor series and Maclaurin series are expressed in that way. Okay. So in this to make sense out of this one, okay, it means that for you to be able to evaluate e raised to x, you have to find the entire sum of this. So there is an infinite number of terms here. Okay. There's an infinite number of terms. Okay. For you to be able to find e raised to x. Okay. But that is not the case because what we will do is we will just add the first n terms of this series. Say, for example, we will add the first 16 terms. Okay? So, that means that we will have to add 1 plus x squared over 2 plus hanggang makarating tayo ng x raised to 16 over, this is not times, that is plus. So, plus x raised to 16 over 16 factorial. So, we'll just add these things. Okay? And this becomes n, this becomes the number of terms, this makes the number of terms 16. Compare nyo yan dito sa infinite number of terms. Okay? In that case, we are truncating. We are truncating the procedure. This is an exact procedure that is adding the infinite number of terms of this series. That's the exact procedure. But the approximate procedure or the truncation that we will commit is by adding only 16 terms of that infinite series. Okay, so that is truncation. Okay, that's the process of truncation that we will use in this context. Okay. Pero again, tama yung term na truncation dito sa part na to. Okay, still this is called truncation. Okay, pero para mapag-iba lang natin siya, we will call this chopping off and we will call this part truncation. Okay. So that's the other error that we will study, but probably on the next activity na to. Okay. Now, so we will deal with approximation errors lang dito. Okay, so since we're dealing with the errors on numbers, okay. So the results of calculations known to be subjected to a certain degree of truncation error, rounding off error. Hindi to truncation error. This is chopping error. Okay. Or basically kahit naman sa truncation error. Okay. In terms of in terms of this context. Okay. So pwede natin siya isama din dito. Chopping error, rounding off error, or truncation error. Okay. Or all of them. Okay. will deviate from the exact or true value of the results of the error-free calculations. Okay. So if the true value of the um of that calculation that we are looking for is x, okay, if that is a true value, and this is an approximate value, that's x, that's small x, this is uppercase x, lowercase x, okay, then the true value and the approximate value would differ by a certain amount of quantity which we will call e of t or et. This et is now the true error. Okay, but remember that this x is the true value. Okay, so that is why the error that we will be obtaining is the true error. It is the exact value of the deviation of the approximate value to the true value. Okay, so ito yun. This is your true error. Okay. Now, if we actually take into account this the magnitude, kasi for example, in this case, an error of 1 centimeter is more significant if a revet, okay, is being measured. Or revet pala, sorry. Revet is being measured. Okay. Why the same measurement is insignificant? Yung 1 centimeter na difference between or that is incurred, for example, in a 10-kilometer road, okay, is actually insignificant. I-compare mo yan sa, for example, 10 centimeter na revet. Okay. So, kasi malaking difference yung 10 centimeter at saka yung 1 centimeter. Okay? Kung pinag-uusapan mo, maliit na bagay. Okay? Pero kung pinag-uusapan natin is 10 kilometers, 10 kilometers, tapos makaka-measure ka ng 1 centimeter, napakaliit lang ng 1 centimeter kumpara mo sa 10 kilometers. So therefore, if we interpret error that way, iba yung interpretation. So that is why, in order for us to be able to interpret error in any possible way that is conceivable, okay, we will normalize this error, okay, in terms of the true value. So that means that we will have to divide the difference, okay, the difference between the true and the approximate values with the true value. So this is what we call normalization, and the resulting number, okay, the resulting number is what we call the true fractional relative error, because this is in terms of fraction. Pero pag multiply nyo ito ng 100%, this becomes now percent true error. Okay? So, percent true error or percent true relative error, okay, pertains to how much the approximate value deviates from the true value. Okay. There are also times that we would like to take the absolute value of this one. So that whether kasi baka mamaya kasi yung deviation kasi mas malaki yung mas malaki yung naging approximate value. So therefore magiging negative ito. So since we are considering the case ng difference or the relative difference between them, okay, we will take its absolute value, so that whether x is bigger, smaller than the the approximate value is bigger, smaller than the true value, then it's possible that we still interpret the error in the same way. Okay, so you may want to work on this and check that if you actually compute or if you actually consider the true error, okay, the absolute true error and the relative error, okay, in two cases, you might be interpreting the error differently. So that is why we need to express that in terms of the relative value. Okay. Now, here's the problem with the idea of computing the true error. Okay. In most cases, we do not have an idea on what the true value of the answer should be. Okay. In this question kasi, there is a standard that we can benchmark our difference. Okay? Kasi alam natin yung alam natin yung height nung alam natin yung length of the road, which is 100 meters. Alam natin yung length ng rivet, which is 10 centimeters. This is 100 meters, then yung isa 10 centimeters. Okay? There is a benchmark that we can consider. Okay? So at that point, we know the true value x. Okay? But what if we are just we are computing, we are trying to solve a certain problem, and the purpose of us solving a problem is because we want to use the solution to implement that on the particular on that particular problem that we are trying to solve. Okay, for example, if you are to design a parachute that can be used to safely land a space module that is coming back to Earth after its mission outside the Earth. Okay. Um, alam mo yung mga factors. You really know the factors that you need to consider in computing, for example, the diameter of that the diameter of that parachute. For example, ang the purpose why we would design or we would use a parachute for a space model when it lands on Earth, it's to slow it down. Okay, as it descends down to Earth, we want to slow it down. So therefore, you would want to make your parachute large. Okay, para mas mabagal yung Kaya lang, one thing is that as your parachute gets larger and larger, um number one, it might also get you might be able to to make your space module come down in a very slow speed. Kaya lang baka naman sa sobrang laki niya hindi na siya bumaba. Okay? O hindi na siya I mean, liparin na lang din siya sideways. Okay? Kasi when you make your parachute larger, mas malaki rin yung contact niya with air. Okay, so therefore, there's the probability that it would actually be blown in another direction grows larger as you make the parachute larger. And of course, the larger the parachute, the more expensive it is. Okay, so if you are to if you are to compute that one, walang answer key for that. Okay. It's not a problem. It's not like the problem that are given to you in school that there is an answer key. Okay, and there is a solution manual. Okay. Most probably, you don't know the answer to that. Okay. So that is why we are deploying kasi we are computing pero we don't really know if our answer is correct or if our answer is actually a true value. Okay. So iba yung term na true value. Okay, sa correct answer or sa correct value. In our context na pinag-uusapan natin, in the context that we are that we are talking about. When you say true value, this is the exact absolute correct value for a certain problem or certain quantity that we are talking about. Okay, but when you say correct value, okay, this may not be the true value, but this may be the best value that your computer can come up or your calculations can come up, and you are confident that this is somewhat close to what the true value is, even if you don't know that value of that true value was. Okay, so we might consider our answer to be correct. Okay, we might answer to our answer to be correct. Okay, with a certain degree of confidence. Okay, masabi lang natin na correct siya because we are confident that that might be the correct answer. And that degree of hindi correct confidence. Okay. And that confidence actually has some basis din. Hindi naman pwedeng guts lang to. Okay. This doesn't talk about guts, but rather there is also there are evidence also pointing out that your correct value, okay, is actually close to the true value. Okay. So that evidence is determined using errors din. Okay. So yun yung point. That is why in most practical cases, this true error, okay, kapag wala naman tayo pagbabasihang true value, okay, we cannot compute for true error. Okay. So if the true value of the error is impossible to determine because the true value of the quantity that we wish to identify is also not is undeterminable. Okay. Then we might as well approximate it in a systematic way. Okay. So the error is approximated then. Okay. Now the relative approximate error EA can be computed as the approximate value over the approximate error over the approximate value. Okay, and can be expressed as a percent error, okay, or percent approximate error. By the way, ito yung percent approximate error, percent, we call this as percent approximate error. Okay. Pero, in most cases, yung percent approximate error can be simply referred to as approximate error na lang. Okay? Approximate error. And also, in a much later discussions, baka i-refer na natin itong approximate error as simply error. Especially when we're talking about the numerical methods themselves. Pag nasa numerical methods talaga tayo, we will say the approximate error is simply the error that we are talking about. Okay? Kung gusto natin sabihin yung true error, then we will qualify it as true error. Okay? But when you say error, it should refer to approximate error, not the true error. Okay? So, para mas madali yung usapan natin. Now, there are many ways, and actually, the computation of this approximate error depends on the context that we are putting it into. Okay. For example, if we're talking about numerical methods, okay, this approximate error can actually be applied to iterative calculations. Okay, and when you say iterative calculations, okay, when you say iterative calculations, it means that you have a certain value x, okay, which say for example has an index I, okay, and then you use this so this refers to the value of x at I, okay, so this is the value of x at I, xi, okay. Now when you say iterative calculations, it means that your calculations tries to compute values, okay, by using the previous result of its calculation to generate a new value for your calculation. Okay, so halimbawa, we produce for a certain part of your iterative calculation, we produce xi at the iteration. Okay. Okay, so which means yung xi plus 1, it means the value at the I plus 1 iteration. Parang ito yung round ng calculations natin. Ibig sabihin, ulitin natin yung calculations that generated xi, pero this time may babaguhin tayong ilang parameters, and may babaguhin tayong ilang aspects of your calculations, and at the same time we will use this as a basis para dun sa next calculation natin. Okay. This is one of the more common algorithms that you would use when you study numerical methods, dahil marami sa mga algorithms that we will have to study are iterative in nature. Okay. So ayun, nire-refer natin ito. Okay, ito, this one. Itong xi plus 1, okay. We may refer to this as the current value. Okay. We may refer to that one as current value. Yung term na to is not absolute. This is actually depending on how we talk about Okay, pero in the context we would like to apply it to, we call this as the current value. Then we will call this as the previous value. Okay, we will call this as the previous value. Okay. Now, we can actually use the idea of approximate error in this, or the error in this case, by computing an approximate error of x, okay, in terms of this formula. That is the current approximation xi plus 1, or the results of the iteration, okay, minus the previous approximation, which is xi, okay, or the results of the iteration, okay, divided by the current approximation. Okay, so we can use this we can use the idea of approximate error in this case. Okay. Okay, so natin siya ngayon gagamitin. Okay. Well, what do we use this with this one? Okay. Most iterative calculations kasi require that your results actually approach a certain value. Okay. We call that in mathematics as converging. Okay. What you would like for your iterative calculations to happen is that as you actually increase, okay, as you actually compute your or as you execute your iteration, okay, the results that are being generated by your calculation becomes closer and closer to a particular value. Okay? For example, meron kang x1 is your first result of your iteration. Okay? Yung x2 yung susunod diyan. Tapos yung x3 yung susunod dun sa x2. Tapos yung x4 yung susunod sa x3 and so on. Now, if your iteration is said to be converging, okay, it means that x4 is close to x3. Okay? So that its difference minus x3, okay, is actually less than the difference of x3 minus x2. Okay? So, habang dumadami yung number of iterations mo, for example, x5, dapat yung x5 is close to x4 in such a way dapat yung closest nila is closer than what is x4 minus x3 is. Dapat yung x4 mo, x5 mo minus x4 should be less than x4 minus x3. Okay? So, which means habang dumadami yung number of yung nako-compute mong value, you are getting closer and closer to a certain value. Okay? So that's the idea. Okay? Which means that if you actually compute error in each stage of this iteration, okay, that error should be getting smaller and smaller. Okay? Now what we do is that we will use that idea na palapit siya ng palapit to a certain value and therefore EA is getting smaller and smaller until it approaches zero. Okay? We may set a certain criteria, okay, in order for us to determine when to stop the iteration. Okay? Kailan natin or at what point do we are satisfied enough that the iteration actually has an answer or the algorithm has an answer. Okay? And that we will use this kind of criteria. So makikita nyo ngayon yan, later on, this is yung general iterative algorithm. Okay? That we will use this as one of the criteria in order for us to determine that we have reached a certain level of error that gives us confidence that our answer is actually approximately okay. Pero actually hindi natin sinasabi na tama yung answer na yun. Or in any way true siya. It's close to true value. Okay, what we're saying is that it converges to a certain value. Okay, but whether that answer is true or is correct or not actually depends on so many other factors pa. Again, the idea is hindi dahil sa nagra-run yung program niyo, even if your program executes properly without errors, it doesn't mean that the answer generated by that program or algorithm is correct. Okay? So ang sinasabi lang that when our approximate error approaches zero, it means that your iteration is converging. Therefore, you are getting a certain value. Now, that value, okay, may be correct, maybe not. Okay. Depending on other interpretation or that is subject to interpretation pa. Okay. But again, if you're either kasi one requirement of your is to first converge. Okay. One requirement of your iterative algorithm is for it to first converge. Okay. If it doesn't converge, then mas talo kayong wala makukuha sagot. Mas talong mali yung makukuha ng sagot if it doesn't converge. Okay. So it should be convergent at first. Okay. So it means that the approximate error should become zero. Okay. And it becomes it, and it does because it becomes zero. We can then interpret the answer, okay, as something is that our iterative calculation has been convergent, okay, and therefore the answer that it would give is actually an answer or a result that contains a certain number of significant figures. Some of those numbers have certain digits and some other are not. Okay. So we can actually make the stopping criterion as something that is lower than a certain value of tolerance. We call this ES, or we use the notation ES for that. Okay. This is the tolerance. Okay. Okay, that determines how precise we would like our answer to be. Okay. The lower this tolerance is, okay, the lower this tolerance is, the more precise your answer becomes, or the results becomes. Okay, because actually this tolerance is related to the number of significant figures in the answer. Okay, and this is the relationship. This is the this is in terms of percent ha. Okay, in terms of percent tolerance, the number of significant figures is related by this expression. Okay? So again, pag mababa itong tolerance mo, if this tolerance is low, is small enough, okay, the tendency is for your precision to be higher. So it means that the lower the lower is this, the more significant figures your answer has. But its trade-off is again, the lower the tolerance, the longer the time it would take for your approximate error to actually reach a value lower than ES kasi nga mababa siya. So hindi natin alam kung ano yung rate of which your iteration produces approximate error that is going down. Okay? So if it actually is very slow, okay, mabagal siyang mabagal siyang itong EA ninyo, mababang mag-decrease until mag-zero siya. Okay. It would take time for your computer to generate an answer. Okay. So ang trade-off niyo dito is yung tolerance which with increase in precision versus yung time. Okay, time for calculation. Because it means the higher the precision, mas mahabang time din to for your computer to come up with an answer. Okay, so you should remember this and this. Okay. Especially itong dalawang to, gagamitin nyo later on sa problem set that is seen below this at the end of this activity. Okay. Okay. Now, here is where we present a pseudocode, okay, for a generic iterative calculation, okay, which you can use as a guide when writing iterative algorithms, okay, guide but not the general rule, okay. So syempre every iterative algorithm requires special cases or special something in them, okay, that separates them from others. Okay, so pero in general, some of this the idea that you can get from this pseudocode, okay, it can be applied to almost all of the iterative algorithms that we will be implementing in the future. Okay, by the way, when you say pseudocode, it's a code, pero it's the things used here, okay, or the things or the syntax here is actually may or may not actually apply to the programming language that you are to use. For example, marami diyan hindi mag-apply sa MATLAB. Okay. And marami diyan hindi many of these things here are not really consistent with the syntax in MATLAB. Okay. Pero ito yung idea. Okay. This is the idea that the pseudocode would wish to convey. Okay. Usually your pseudocode would require three inputs. Val, these are variables hindi to laging fixed. Okay. Three variables. One is val, two is ES, and three is max IT or max it. Okay. Ang variable na val, okay, is a value, okay. Normally, it's either an initial value given in a certain problem o kaya it's a guess. Okay. Some of the iterative algorithms that we will discuss involves trying to first guess. Okay, trying to guess first a certain value for So this can be arbitrary, depende sa user. Okay. That's the value val. Okay. ES is the tolerance. Okay. As mentioned in the previous discussion. Okay. And again, this tolerance depends on the number of significant figures that your approximate answer might probably have in the end. Okay. So related just a number of significant figures. So you might want to use a certain level of tolerance so that your answer is correct to, for example, is expressed to, say, for example, 5 significant figures. Okay. So that is ES. And then max is the maximum number of iterations. Okay. Well, you can think of iterations as a step kasi basically this would loop, i-loop natin siya. Okay, this is a looping process. So when you say looping, if you're done with if you're done with activity 0 and activity 1, okay, pwede kayong gumawa ng for loop, okay, which places a certain number of iterations or loops, or implements your loops in a certain number way. So naka-fix yun pagdating sa for loop. While yung while loop, okay, uses naman um, uses decisions, okay, in order for it to cease operation. Okay. So we are most of the iterative most of the iterative algorithms um, recommends that you place the maximum number of iterations as one of the stopping criteria. Okay, actually these two variables would be used as part of the stopping criterion of your loop. Okay. Yung isa doon is actually the maximum number of iterations, and is always recommended that you implement that. Okay. Not unless you know that your loop would terminate using a single stopping criterion. Okay? So kung hindi kayo sigurado sa convergence, okay, ng loop ninyo, if you're not really sure about how your loop would converge, okay, then it is recommended that you put the maximum number of iterations to be one of the stopping criterion, so that when your loop runs after a certain number of iterations, it stops, or it exits. Okay, and not put your computer in limbo. Kasi what would happen is that kapag hindi kasi siya halimbawa, hindi nag-converge yung loop ninyo, okay, your iterative algorithm did not converge. And say for example, the reason is it's because it cannot meet the tolerance criterion. Then your computer will just keep on computing and computing. Okay, until mapuno niya yung memory niya. Okay, and then it would crash. Okay. So we don't want that to happen. So we would like to put in maximum number of loops, or maximum number of iterations that your computer will do, or that your algorithm will do. And then it stops after that. Okay. So since you'll be using decisions in order for your loop to stop, okay, we will probably be using the while loop more, okay, compared to for loop. Okay, we will use loop kasi if the number of iterations that we can use is fixed. Kung mapi-fix natin yung number of iterations, okay, and if there is no other stopping criteria but the number of iterations, then we can use for loop. Okay. But in the cases that we are, in most cases, we will be using decisions. We will be using criteria to stop the iteration. Okay. So, ayun. So, first you initialize everything. Okay. As the number, this talks about the number of iterations. This would keep track of how many iterations that your loop has done. Okay. The variable sol holds the solution, okay, which you will initialize to the value of val. Okay, again, it may be an initial value as per problem, or it may be an initial guess, okay, from the user. Okay, and then your EA. Okay, we will set EA to 100, means 100%. Okay, so that at least kasi if we don't initiate EA, baka mapunta sa point that your EA becomes less than ES kagad. So therefore, hindi mag-execute yung loop ninyo. Okay, so that is why it is recommended that you initiate this value to 100. Okay. And it's possible that that the error actually reaches more than 100. Okay. Possible naman yun sa but in the case of the formula, hindi pala pwede. Okay, sorry. In the case of the formula that it will use, it will not be able to reach more than 100. So the 100 is the maximum that it can reach. So we set it at 100. Okay. And the aim is that that's EA approach 0. Again, for your iterative algorithm to work, it should converge to 0 by having your EA decrease down to 0. So we start with 100. Okay. Now we start with the loop. So iba-ibang programming language use different syntax for the loop. Okay. Makikita nyo later on sa mga example programs that I have used here. Here except for the problem set part, you would be exposed to the programs, to the scripts. Okay. You would be exposed to the scripts, and I would just like you to interpret the script. Okay. Pero later in later activities, hindi na ako masyado magbibigay ng script. Okay. I would be more of like asking you to write one to solve that problem. Okay. So dito, baka next time ang bigay ko na lang puro pseudocodes na lang. Okay. Pero in this case, in this activity, I made it a point that I write the scripts here first. Okay. For you to have an example or examples of how iterative calculations are written as algorithms. Okay. So do your best to interpret them. Okay. In order for you to be able to apply them to future topics. And again, most of the iterative algorithms, kung iterative algorithm naman yung pag-uusapan natin, most of the iterative algorithms tend to have the same principle used. Meron lang siya mga iba-ibang things. Okay, there are some things that are really that separates a certain algorithm from the others. Okay, pero yung general concept ng iterative algorithm is the same. So the way that we write them is actually the same also. Okay. So ayan. Now, so yung do here, this do initiates the loop. Okay. This is a decision loop. Okay. So if you're talking about MATLAB or Octave, that might be equivalent to while 1. Okay, because while takes in a certain decision. So in this case, ang gagawin natin technique is we will set the condition inside while as 1. Then we will just use an if statement to express the decision. Okay? Pakikita niyo 'yan doon sa mga sample programs natin later on. Okay? So that's one way that we can implement the while loop. Okay? So ayun. Now, kasi madalas medyo nakakalito rin kasi yung if you actually put the decision criteria here. Okay. So most may mga books akong nire-refer that actually writes a one line if decision statement as a way to implement the while loop. Okay. Which is actually more is easier to understand compared to writing the decision here. Okay, but I don't know which is more efficient. I think mas efficient yata in terms of computation yung nandito yung decision criteria kaysa meron siyang if statement. Okay. So I don't know kung pero as a practice, ganito muna yung gawin natin. Okay. Now, the first step is to actually put the previous value in another container or in another variable. Okay, because you would use this value as part of the calculations for the next calculation. But then you would use the same variable. Okay, para hindi ka paulit-ulit ng formula. Okay, so you would use the same variable. So after which pag na-assign mo na yung old value yung previous value dun in another container, then compute the new value for that. Okay? So in that case I think you may have to erase this part. Okay. Nakalimutan ko i-erase dun sa I think you have to erase this part, and then you just look at this one. Okay, so this one is this line contains actually the formula to compute the sol, the variable SOL. Okay, which based din sa which dapat ma-involve itong sol old in that at that point. Okay, or pwede namang hindi. In general, dapat ma-involve siya kasi because it's an iterative algorithm. So therefore, the calculation of the new value depends on the old value. Okay. So, may involve ito more or less dun sa calculation ng sol. Okay, and then update iter, the number of iterations. Okay, now specify your no, this is where you compute your approximate error. You would approximate you would compute an approximate error. Okay. Given that the solution is not equal to 0, because if the solution becomes 0, then that complicates the math. Okay. So, may gagawin tayong iba kapag yung solution nyo becomes 0. Okay. And then, this is your stopping criterion. Okay. So, if your EA is less than or equal to the tolerance, or, okay, or, you would use or, the operator or, the number of iterations reaches the maximum. So, it's greater than equal to, okay, then we exit the program. Okay. And then we write the solution to your function. Okay, so that the function would return the value of the solution. Okay. So again, to summarize, initiate 3 values. Okay, the solution, the iteration tracker, and the approximate error. Okay. Then inside the loop, okay, first pass the value of the previous calculation to another variable, then compute the value of the new variable. Okay, update the iteration tracker, okay, or the iteration counter, compute EA, okay, and then implement your stopping criterion, or implement your stopping criterion, okay, and then finally, if it needs to, pass the value of your solution to the function so that the function would return the value of the solution. Okay. So it was explained here. Okay. So yung explanation that I gave you is also right here. So kung medyo nalabuan kayo sa sinabi ko, you may actually want to read this paragraph. Okay, in order for you to understand this one. And it is really imperative that you understand this process, because this is most of our task would be revolving in in writing iterative algorithm. So at this point, it is imperative that you really have to study this part. Okay? So ayun, yun yung gusto kong sabihin dito. Okay. Now, at this point, okay, the activity now shifts to demonstrating, or it would in presenting how error is manifested. Okay, how error is manifested in different cases. Okay, so I think I could leave this to you. Okay, I could leave this discussions with you. Okay, and again, at this point, you would not really be writing you would not be really writing scripts. Okay, they would be given to you. Okay, your task is to study those scripts, so that when it comes to this part, like for example, this problem set, which requires you now to write iterative algorithms, okay, for infinite series, such as this one and this one, okay, you would be well versed with how to write them. And actually, you can actually base the scripts that you would use here for scripts to the scripts that were given as an examples in the previous parts. Okay, but the thing is that you have to practice writing them. Okay, so and actually, in terms of MATLAB and Octave, this is something that I would like to be reminded. Okay, there are actually two ways to present your results. Okay, and that actually plays a role in how your iterative algorithm is written. I have here a script. For example, this one. Just this one. Take a look at this one. This is an iterative algorithm. Okay. That reports only the results. Okay. It reports only the results. Same thing with this one. Uh, Same thing with ayun lang pala. Okay. So, ayun. So, this is one kind of of an iterative algorithm that would just simply return the result, the end result, okay, of your iterative algorithm. So it simply returns the answer. Okay, so this is for example, this returns the value of someone, okay, which is the final value of your iterative algorithm. That's one way to write your algorithm in MATLAB or Octave. But what the thing about MATLAB or Octave is that since you can actually put everything into array, okay, this is another way to write iterative algorithms in MATLAB or in which case now it presents your results in a table. Okay, it presents your results in a table. Nakatabulate siya. So nakatabulate dyan is yung iteration number. Okay, so it means ito yung iteration 1. Okay. And then the what was tabulated there was term and sol, which means what's the value of the term, okay, and what's the value of the solution. Okay, so nakatabulate siya that at the first iteration, this is the value of the term, this is the value of the sol. Okay, at the second iteration, this is the value of the term, this is the value of the sol. Okay, and so on until, for example, the last iteration happened at 50, at I equals 50. So at 50th iteration, this is the value of the term, this is the value of the sol. Okay, so this is now the final value. Okay, this is the final value that should be returned by your script. Okay, so in the first case, ito lang yung ibibigay niya sa inyo, this final value. But in this case, ang ibibigay sa inyo is yung buong table because I have, in this case, these things, this term at saka this solve, as you progress with the calculation, you also put them in an array. Okay, you also put them in an array. So that's the second way. Okay, although in these cases, isa pa lang yung stopping criteria that the scripts uses. Okay, in which it only stops if the value of this goes below a certain tolerance value. Hindi pa ginagamit dito yung maximum number of iterations. Okay, mainly because I know that the that the values given here would actually converge. Okay, it would converge on to a certain number. So therefore, I did not at this point I am not considering pa yung maximum number of iterations because I am sure that that program would stop at some point using just the first stopping criterion. Okay, but in the future isasama natin yan, which you would see in as changes dito. Okay, so I hope that that you would be studying this carefully. Okay, because this would be the baseline if the first three activities enables you to use MATLAB. Okay, this next activities should enable you to write programs or write algorithms. Okay, para sa susunod mas makapag-implement pa tayo ng more mathematically complex algorithms. Okay, so that should end our discussion for this activity 3. Okay, so I hope that this to be something that you would be working on, okay, with with more effort, okay, and more perseverance, even if this is kind of difficult for you to work on. But if you persevere, you would be able to learn something out of this. Okay, so if you have questions, feel free to message me. Questions or concerns, feel free to message me, and let us talk about your questions or concerns. Okay, so there.